This is Mr. Rankin, and this is one of your lessons that you need to listen in on for class. This lesson is focusing on soils, which is the next lesson in our sequence of soils in this unit number 5 on climate and water. Teaching point, I'll be able to observe how soil factors can affect the amount of water that infiltrates the earth. Now, infiltration, as we saw on the whiteboard that I drew on, the downward movement of water inside the earth from the surface down to bedrock, that downward movement is called infiltration. Launch. If you had 2 graduated cylinders with holes at the bottom, one filled with sand, we could say maybe this is filled with sand, and the other with marbles. All right, now this is not marbles, but this is big enough, bigger than the sand, and poured equal amounts of water into both. Which do you think would allow water to pass through it the fastest, and explain? All right, so you can pause the video, you can think about it, and then you can unpause it when you're done thinking about it, and you can listen in on the answer. All right, so with respect to this, if you pour equal amounts of water, let's say if I pour in 2 liters, like a 2-liter soda, right? If I have a 2-liter bottle and I pour water in, exactly 2 liters for each, and I pour it into these tubes, right? One filled with sand, one filled with marbles. Right, the water will pass through the marbles faster than the sand, right? And that is because the pore spaces, right, the spacing in between these grains would be bigger than the spacing in between the sand particles, which would allow water to pass through the marbles faster than the sand. Okay, which statement best describes the porosity percent pore space, which was found for these 3 samples? All right, looks like I got to fix that word there. All right, so you have 0.1 centimeters for A, 0.4 centimeters for B, 0.7 centimeters for C. All right, so looking for porosity. Now, porosity is percent pore space. All right, so you would choose A has a greater porosity than B and C. Right, again, looking at the pore spaces, the percent pore space. So like this, this little dot right here and that little dot right there, right? That is the spacing between the grains, right? We see like this area here and that area there for B, and that area there is the pore space. And for C, we have this area here and that area there and this area here. That is your pore space there for C. All right, so you can pause the video. You can think about what is the best answer for this. And then you can unpause once you think you have the correct answer. All right, now we have an abundance of pore spaces for A, but they're small. We have less amount of pore spaces for B, but they're slightly bigger. And we have even less pore spaces for C, but they're the biggest. Now, all these containers have grains that are rounded, rounded, and rounded. We have grains that are packed one on top of the other, right? One on top of the other, one on top of the other. Same thing here, one on top of the other, directly above. Same thing with C, one, they're packed together, one right above the other. So their packing is similar, their shape is similar, and they're sorted the same. This contains all 0.1 centimeters, nothing different. This all contains 0.4 centimeters for B, nothing different than 0.4. And C is all 0.7 centimeters, nothing different than 0.7 for C. Based on those factors alone, right, we should have an answer for this. All right, the answer should be choice D. All three samples had the same porosity. All right, now let's get this down, please, in your notes. Porosity, the percent of open spaces in a volume of soil or rock. Packing, tightly packed, less, loosely packed, more. Now, less meaning porosity, and more being more porosity. So if you have tightly packed sediments, if I go back to the previous diagram, this is all, even though they're one on top of the other, it's considered loosely packed. Now, packing, no matter what, sediments must be packed together. They must be touching each other. Either they're going to be tightly packed or loosely packed. When you have one on top of the other, just like this in A, B, and C, they're all considered loosely packed. Shape, angular, less, rounded, more. In that diagram before, we had all rounded sediments, right? And that would mean you would have the greatest amount of pore spacing, of percent pore space. If you have angular sediments or angular soils, same idea, same concept, the sediments or soils will fit together more like puzzle pieces, and that can reduce the amount of pore space and the percentage of pore space. Sorting. We have poorly sorted, less, well sorted, more. So when a sample is poorly sorted, that means you have a mixture of sizes within it. When it's well sorted, that means you have basically the most similar size in it. You're never going to get in everyday life, if you take a sample of soil, all of the particle sizes would not be exactly the same, but close enough to the size. That's why I mentioned in that diagram here that this is well sorted because that's all the same size for A. B, 0.4, that is well sorted, it's all the same size. And then C is 0.7 centimeters, all the same size. However, if we had a letter D and you begin to mix them up, then it becomes poorly sorted, and then you reduce the amount of pore space. All right, and then size. All right, size does not matter if the packing, shape, and sorting are the same. That was the factor for that last question.
All right, guys, after the last class, I'm still here. It's Friday afternoon, and you guys have all headed off for your weekends, half your luck. I have got a better way to work out the maths on the soil porosity, okay? So on the left, you've got 20 mils of sand and air. Here I've got 20 mils of water. What I'm going to do is just tip a bit of this in.
This is how to calculate your percent
when
pore
that
space.
sinks down, we're going to pour in a little bit more.
Notice how the sand is becoming darker. The water is traveling through the sand, right? So there's no more water at the surface. She's going to pour more water in. Notice that this water will disappear a bit more as it passes through. The base will become darker.
It's doing that weird thing that yours was, Kat. So I am just going to aid it for the sake of this particular thing, because I would quite like to get home on my Friday afternoon as well.
Oh, see the bubbles there. So
There
you
we go.
definitely have
There's
some
the
air
water
pockets.
flowing down through it.
There you go.
Okay, it's seeped all the
Disappears.
way in. So I'm going to add a little bit more until all of that sand is wet. Still a little bit of dry stuff right down the bottom. Okay, so let's assume that that is all soaked in. It's pretty close. So I'm actually going to tip out the water that's pooling on the top there. Okay, so all of the air that was in there is now filled up with water. Okay?
The air
And
was
what we've
pore
got
spaces.
left here is there's 10 mils, 11 mils, 12 mils left of water. Okay, so what that means is that it was 8 mils of water that went in here. That means that there was 8 mils worth of air in that sample. Okay, so
Now here's the calculation.
we grab a random piece of paper. We had 20 mils of air plus sand. We only used 8 mils of water that went in there. Okay, so we know that there was 8 mils of air. So now we go 8 divided by 20, which gives us, without a calculator close to hand, I'm going to say 40%. Okay, so hopefully that system works better for you. Okay, so just recapping, what we did was take our sample, wait till all of the water had soaked into it, and then worked out how much water we had used, and the amount of water that we had used was the amount of air that had been in there, and then we can work that out. Hopefully that makes more sense. See you guys, have a good weekend.
All right, so that's how you calculate the percent porosity. All right, passing through soil and rock, we have permeability. This is a vocab term that you need to know. Now, soil has the greatest ability for water to pass through, unlike bedrock. Right? Very hard for water to pass through rock samples, especially if it's metamorphic, which we'll get into with unit number 7. Metamorphic rocks are heat and pressurized. These rocks are so pressurized that the pore spaces in the rock samples are greatly reduced. And that's why it's very difficult for water to pass through metamorphic rocks. Permeability, the ability for water to pass through the empty spaces, the pores in soil and rock. Again, rocks have pore spaces, just how you have pore spaces in your skin. All right, but they're not as big and large as the spacing between soil grains or sediments. Sediments and soil is similar, right? Because really soil is based on size and color and a few other factors. All right, so we have the greatest porosity in this picture where the sediments or the soils are the biggest. We have less porosity here. We do have the bigger particles, but if you notice, we have a mixture of big and small, which means that this here is more sorted or well sorted, although you do have some different sizes in here. But here is definitely more of the poorly sorted if you compare the two. because you definitely have these smaller sediments or smaller soil particles in between the pore spaces of the larger particles. I don't like this picture that well because they all should be touching each other. You're not really going to have particles that are suspended, right? But anyway, this is for the sake of just visual. So these smaller sediments or smaller soil particles reduces the pore spacing and therefore would not have the ability for water to pass through it faster. Water will pass through, but not as fast. All right, moving on. You have higher permeability means a higher rate of infiltration. The greatest porosity, loosely packed, rounded, and well sorted, and large sediment size will result in more permeable soils. Not percent porosity, but more permeable soils. Loosely packed, one on top of the other. Not closely packed. Rounded sediments, not angular. Well sorted, basically almost the same exact size. And your largest sediments will have the greatest and biggest pore spaces. Right, so according to your reference table on page number 6, if you go to that page, look at the upper right-hand corner of page 6, and you colored in a few of these areas. All right, so we have boulders, we have cobbles, we have pebbles, we have sand, we have silt, and we have clay. And if you look at the ranges of these sizes, we can see that sand grains are bigger than clay grains. This would have smaller pore spaces. Water can pass through, but not fast. Sand grains, water can pass through, but faster than clay. But sand is not the fastest. Can you guess what the fastest would be based on page 6? And yes, the answer there is boulders. So if you had a soil composed of boulders sized, then that would definitely have water pass through it the fastest. All right, the experiment is testing porosity. The results of the activity should have indicated that approximately equal amounts of water were added to the cups of. All right, so here we have sand grains, silt grains, pebble grains, and a mixture of sand, clay, and pebbles. So which one of these would you pour in equal amounts of water to fill up all of the air spaces in these samples? Think about it, pause the video, and once you have your answer, you can unpause it and listen to the answer. All right, so if you pour in equal amounts of water, let's say, for instance, if the sand needed 50 mLs, or 50 mils, like in the video, 50 mLs of water, the silt would also have 50 mLs of water. And the pebbles would also have 50 mLs of water. More than likely, in each of these, very hard to put these real sediments loosely packed. So more than likely, all these 3 samples are probably going to be tightly packed. So they're all packed the same way. More than likely, they're all going to be the same shapes. Maybe they're all going to be rounded or sub-rounded. And it's all the same size. This is all sand grains. This is all silt grains. This is all pebble grains. Right? However, the mixture of sand, clay, and pebbles now reduces the percent pore space. So we would need less than 50 mLs of water to fill up these pore spaces. So this would have the lowest percent pore space. Mixture, different sizes, poorly sorted. All right, let's just take a look at this, and we'll explain. All right, if a soil has high permeability, water can pass through it pass right through it easily. However, there's always a but. If a soil has low permeability, water cannot easily pass through it. So remember, permeability is the ability of water to pass through a substance, right? Substance meaning a soil or rock. Soils with high permeability, the ability for water to pass through it faster than low, would have soils that are rounded, well sorted, and loosely packed. Right? Those three factors will allow water to get through it fastest. Soils with low permeability would have soils that are angular. Angular has sediments or soils that fit together very well like pieces of a puzzle. Poorly sorted, all mixed up in terms of size, and tightly packed. One on top of the other, but we're dealing with almost like a rhombohedral type of packing. Soils with low permeability would be a concern for flash flooding, right? So if water cannot get through the earth because of low permeability, perhaps maybe it's a clay soil, then we have the risk of flash flooding at the surface, right? Not too good. All right, ladies and gents, that is your class. I can further explain tightly packed next time around. All right, have a great day. I'm going to ask that you complete some work based on these lessons. Thank you.